Okay, welcome to the set theory seminar. It's a great pleasure to introduce Monroe Eskew as today's speaker. And he's going to talk about the approximation property and generic embeddings.
Thanks very much. So I'm going to talk about some work in 3 different papers. One solo paper and then one with Sean Cox, one with Vera Fisher. And the point is to highlight the use of a certain the use of the approximation property. I mean, it's not always the same argument, but we'll see what happens. Okay, so most of you know this history. Joel Hampkins defined the approximation property in his thesis, I believe. And so 2 of the famous results of his about this were this super destructibility theorem. And this says that small forcing, of course, it preserves large cardinals, but it makes them fragile. So if you add a generic for a small forcing smaller than kappa, then after that, kappa, even the weak compactness of kappa is destroyed by any non-trivial, any kappa closed forcing that adds a new subset of kappa. And there are generalizations of this for maybe it doesn't add a subset of kappa, but subset of something larger, and then it would destroy that level of supercompactness. So this is a very interesting theorem. And then there's this other one that says that kind of the standard strategies we have for preserving large cardinals through forcing are in a sense like the only ways to find witnesses to the large cardinal properties. So this says that, okay, he stated it differently, but essentially if you have a cardinal kappa that in some generic extension is the critical point of a definable embedding, or we can just say it has, so not just some generic extension, but a nice enough one, namely the larger model and the smaller model together satisfy this delta approximation and delta cover property, then in fact, J is a lifting of an embedding definable in V. So the restriction of J to V is actually definable in V. So then this property was used for some other well-known results. So this approximation property led to the notion of guessing models. And this was studied extensively by Christoph Weiss and Matteo Vialli, and their big theorem was that it's almost an equiconsistency result about PFA, but it says that if you force PFA in a standard way, where the standard way can be the following: kappa is inaccessible, and you have a forcing with the kappa approximation property that turns it into omega 2 and makes PFA true, then kappa must have been strongly compact. Now, okay, it's still, I guess the proof of PFA assumes supercompactness, but it's close, right? Proof of the consistency. Okay, and then if you read the proof of Wooden's hot dichotomy theorem, you'll see that the approximation property is also playing an important role. So remember, this is a theorem that says, fairly recent result in the last decade or so, if there's an extendable cardinal typo, then either every singular cardinal above this extendable and their successors are correctly identified as such by HOD, or every regular cardinal above delta is measurable in HOD. Of course, this is a very hot topic. Okay, so what is this approximation property? So I'm going to tell you what it is in a slightly non-standard way, because we're going to use the first paragraph there on its own later. So suppose A is a set, and you have X a subset of A, and then you have F class of subsets of A. And we'll say that X is approximated by F when, for all little a in F, A intersect X is a member of F also. So this is a kind of local instance, and we'll use this later. So for models of set theory, M contained an N and an M cardinal kappa, we say that the pair Mn satisfies the Kappa approximation property when for all ordinals lambda in M, if set X, subset of lambda in the larger model, is approximated by the p kappa lambda of the smaller model, then in fact X is a member of the smaller model. And we say that a forcing has the Kappa approximation property if it forces that the pair V, Vg has this property defined more abstractly above. Okay, so there are many forcings that have the Kappa approximation property, but it's a bit not trivial to show it. So, okay, a definition isolated by Usuba that gives a nice class of forcings with this property is given by the strong kappa CC. So he says a poset has a strong kappa CC. I'm missing a clause there. It's supposed to have the kappa chain condition and doesn't force any branches to kappa Suslin trees in V. So this is, yeah, it's just by definition, it should include the kappa CC. Okay. So, so this is actually a pretty broad class of forcings. And so, for example, if P is kappa CC and there are no kappa Suslin trees, then it's strongly kappa CC. If P squared is kappa CC, then it's strongly kappa CC just because a Suslin tree squared, it's well known that this is not kappa CC. A Suslin tree, just to remind everybody, is a kappa CC forcing. So it's a kappa tree that just as a partial order has the kappa CC. Also, it's not hard to show that if P has a stronger chain condition than kappa, then it is strongly kappa CC. So if it has a delta CC for a smaller cardinal delta, yeah, this is not hard to show. So Usuba proved this kind of optimal result about the Kappa approximation property, at least along the dimension of Kappa CC. So there are other ways to have Kappa approximation, but he showed that if P is a non-trivial and Kappa CC forcing, and Q dot is a P name for a Kappa closed forcing, then the two-step iteration P star Q has the Kappa approximation property, if and only if P is strongly Kappa CC. So, right, it's the only if direction is the easier one because Kappa Suslin trees do not have the Kappa approximation property because it's easy to see that they're both Kappa CC and Kappa distributive, so they don't add. The generic branch is, or you can see it directly. The generic branch is something that's approximated, but Kappa approximated, but not a member of V, of course.
Monroe, could I ask quick? Do you mean that is the assumption that the equivalence is between the statement that P is non-trivial and Kappa CC, and for every Q dot that is Kappa closed, P star Q has the Kappa CC, has the Kappa approximation property? That statement is equivalent to saying that P is strongly Kappa CC. Is that it, or? Because it's unclear what the quantifiers here are like in this statement.
Right, sorry. Yeah, it should be that, exactly that. So if, okay. Yeah, if P is strongly Kappa CC, then every Q will have P star Q with the Kappa approximation property. On the other hand, if it's not strongly Kappa CC, then you can just, then there exists a Q. So you can just set Q equal to the trivial post set. So that's a good thing to notice, that Q can be trivial in this theorem statement.
Okay.
So, okay, so the first application of mine is this compactness versus Hugeness at successor cardinals. So the theorem is the following. This is with Sean Cox. Suppose Kappa is a regular cardinal, and now we're going to talk about Kappa plus. And we assume that 2 to the less than Kappa is less than or equal to Kappa plus. So this is not the GCH, this is one cardinal away from the GCH. And suppose there's a weakly presaturated ideal on Kappa plus concentrated on cofinality Kappa. So I'll tell you enough information about that to give an outline of what's going on, what that means, weakly presaturated. So then the conclusion is weak square Kappa holds. So this result came about after trying to find the consistency of the opposite. So we wanted to get a model where there's a saturated ideal on omega 2 and the tree property at omega 2 holds. And we thought probably this could be done with the continuum being omega 2. So this says that we can't do it. You cannot do it with the continuum being omega 2. We don't know yet if it can be done with continuum omega 3, but all the strategies that we know of will not work. So this is a limitative result. So what is weakly presaturated? We say that a normal ideal I on cardinal Kappa is weakly presaturated when, if you force with P Kappa mod I, then that comes along with a generic ultra power embedding. So you can always do that. You don't have to have a well-founded target model. But this assumption says that Kappa goes to Kappa plus. So this is a consequence of being saturated, but it's also pre-saturated, and we're not actually assuming that Kappa plus is preserved by the forcing. We just want Kappa to be sent to Kappa plus. Okay, and just to remind you what weak square is, there's a sequence, script C alpha less than Kappa plus, and each C alpha is a non-empty set of size at most Kappa, consisting of club subsets of alpha, and each has order type at most Kappa. And you have this coherence. If you have D and C alpha, and beta less than alpha is a limit point of D, then D intersect beta is a member of C beta. So this is relevant to the tree property because Jensen showed that it's equivalent. The statement weak square Kappa is equivalent to the existence of a special Kappa plus tree. So a counterexample to the tree property at Kappa plus. Okay. So I want to give you an outline of the proof without doing all the details, just to show you where approximations are used. So let's just describe the setup. So we assume you have a weakly presaturated ideal on Kappa plus, concentrated on cofinality Kappa. And let J from V to M be a generic embedding as in the hypothesis of weak presaturation. So you do some forcing to get this J. Now we'll work in M and construct a weak square Kappa sequence. And the critical point of this map is Kappa plus. So this will reflect to V, showing that it already holds in V because M
So are you
satisfies
assuming the ideal is Kappa plus complete? That's part of the definition.
Yes. So I'm assuming it's a normal ideal. Yeah. The assumption of normality is going to be also used for the fact that it concentrates on cofinality kappa, that tells us something about what happens in the ultra power. So here's the setup. So let delta be kappa plus of V, and it's the critical point of J, and by the concentration on cofinality kappa, M will satisfy that the cofinality of delta is kappa. So this may not hold in the full forcing extension, but that doesn't matter for us. So we assume in the hypothesis of the theorem that 2 to the less than kappa is kappa plus or less. So we have delta to the less than kappa is delta. And therefore, the p kappa delta of V is a member of M. So this is because you can just list it out and then apply J to it and then restrict to the first delta members, and that's the same object. So in M, we can use this set to define this sort of local instance of approximation. So let's just say script A is the set of all subsets of delta that are approximated by p kappa delta of V. Now, for this argument, I just want to emphasize that we're not going to use anything about the approximation property holding between two models. We'll just use we'll just use the definition. But I think it's kind of still significant that, I mean, in my opinion, sometimes the definitions you come up with or use are kind of most of the work. And so this is the key thing. Like, we're going to use the notion of being approximated at this local level. Okay, so the next step is in M, of course, delta has cofinality kappa. So just fix a club in delta witnessing this. I give some names to things, but I won't actually need to refer to them. But also we're fixing a sequence of surjections from the ordinals from kappa to the ordinals of cardinality kappa. And by the same reason as p kappa delta V is a member of M, also this sigma vector is a member of M. So then we take an elementary submodel using these objects. So just, it only needs to be elementary in the H sub J delta of M, which is, this is the kappa plus of V. I guess I actually have this little highlighter. So yeah, it looks nice. Okay, so and just take these objects. So C star, p kappa delta V, and this sequence of surjections sigma vector, and make sure it has all the ordinals below delta. But it's going to have, we want it to have size kappa, which is okay, of course, because delta is collapsed to kappa because it's the successor of kappa and the critical point of the embedding. Let's look at the p kappa delta of this model. That's Q. Okay. Okay, next. So there's some, so I need to introduce a notation. So suppose X is a set of ordinals closed under the good old pairing function, and Y is a subset of X that codes a pre-well ordering of type some ordinal alpha. Okay, hopefully we remember pre-well orderings. So just for this kind of situation, write F sub Y to be the coded surjection. So this, you have a subset that tells you how to order the objects of X in some pre-well order, right? So that is equivalent to having, there's a natural correspondence between having a surjection onto the length of that pre-well ordering. So the key claim of the argument is the following, which is basically, if you know how to prove that weak square follows from CH, we say that you can basically do the same thing here. Okay, but working in M, right? So the thing is, so if you have any two sets that are approximated, this is key, and they code well orderings of delta of the same length, then the set of all images of members of P kappa delta under f sub x is the same as the same set defined with y. So you have this kind of, you can sort of define P kappa delta of V, right? Just using some surjection, right? If you use one from V, here's the point. If you use one from V, and instead of P kappa delta N, I put P kappa delta V, then you're going to get P kappa alpha of V, which is whatever length the pre-will ordering has. The problem is like that M doesn't know what these objects are. So we have a kind of surrogate for M that's definable in M, and they end up being canonical. Okay, so, okay, I won't do the details of this claim, but I just want to say that it's important for it's like a key thing for the argument. We're going to use in this claim, the proof of it, the fact that the cofinality of delta equals kappa, and that's important to get a club of Z contained in delta such that at least the images are the same. F sub x image some small subset of delta and f sub y. These Z's in the statement here, they may not actually be in V, okay? But that's okay. I mean, then we need to cover them by a set in V. And that's also, we can do that because it's a set of size less than kappa, and the cofinality of delta is kappa, so we can do that. So those are some key points in the proof of the claim. Okay, then to finish up the argument, the construction, just in brief, we define the weak square kappa sequence as follows. So we first define it for small cofinalities less than kappa, as basically these sets, except we throw away the things that are not appropriate. So you just take this and then you intersect with all the clubs in alpha of order type less than kappa. So that's definable, that's okay. Well, but what X do we use? Well, we can use anything because it doesn't matter. According to this claim, the choice is irrelevant. We get the same collection as long as it's using a coded surjection that's approximated. And we have to take care of the ordinals of cofinality equal to kappa. In that, we have two subcases. Either they used to have cofinality delta, or they used to have cofinality kappa in V. But in either case, we argue that there exists a club of type kappa such that all initial segments take this form. They are the image of something in the P kappa delta of N by some approximated surjection. And M, the funny thing about the argument is that this splits into two subcases. M may not have any uniform way of telling which ordinals of cofinality kappa used to have a larger cofinality and used to have a smaller cofinality. I mean, it doesn't even have the ability necessarily to ask the question, but you just say, in either case, there exists a club with the property, so M can just choose one. So that's how the construction goes. Okay, that's the outline of that argument. Are there any questions about it before I go on to the next thing? Okay. All right, so now I want to talk to you about another work with Vera Fischer. And this is about a quite different topic, but there's an argument in the paper where we use the approximation property, and so I thought it was interesting to, in a quite different way, but I wanted to show how it comes up again. So we study the notion of strong independence. So we have many different notions there, but for a cardinal mu and a family of sets contained in the power set of some set S, we'll say that it's mu free if all Boolean combinations yield a non-empty set. So you take two disjoint subsets of your family of each of them of size less than mu, and then with the first one form the intersection of everything, and then the second one form the intersection of all the complements, and then take the intersection. So we want to say that that gives you a non-empty set. And of course, partial functions from the family to 0, 1, defined at less than mu many points, will code such an operation. And so for a given partial function p, we let xp denote this Boolean combination, like it's written there. So we say a family is mu kappa independent when it is mu free and for all p in the co-enforcing. So these partial functions are of course elements of the co-enforcing, and of adding cardinality f many subsets of mu. So it says any less than mu Boolean combination gets you not only a non-empty set, but a set of size kappa. That's mu kappa independence. We'll say that a set is a mu kappa maximal independent family, or mu kappa MIF, if it's mu kappa independent family and cannot be, it's maximal with respect to being mu free. And the mu kappa independent spectrum is a set of all cardinalities of mu kappa maximal independent families. Okay, so Vera had studied this quite extensively in several works in the case mu equals omega. And actually, I should say extensively in the case of mu and kappa both equal omega. Then more recently, she started to look with Diana Montoya and then with me at generalizations. So note that using Zorn's lemma, it's easy to show that the omega kappa independent spectrum is non-empty for all infinite kappa. So find some, start with this single set, or start with one of size 2 to make it non-trivial. Okay, then go, yeah. Well, no, a single one is fine. Yeah, that's still will get you. A singleton will never be maximal. So anyway, just applying Zorn's lemma, there will be a maximal independent family. A little more sophisticated argument gets you that, using a kind of famous result on whose authors I can't remember at the moment, but the early 20th century, you can get independent families of size 2 to the kappa, so you can extend them to maximal ones. But in the case of mu larger than omega, the situation is quite different. So this is kind of summarized, this theorem summarizes a short paper of Kunin, and we give a proof of this sort of in our notation and terminology in our paper. So there are many combinatorial consequences of non-empty spectrum for mu larger than omega. And whenever you find one that's not a consequence of ZFC, you know that, okay, well, consistently, the spectrum is empty. Okay, and as you'll see from the theorem statement, consistently, it's empty everywhere except for mu equals omega. So it's kind of a special situation. So a kind of interesting case to first start thinking about is, what about mu equals omega 1? And the first consequence says that, well, then you have to have CH. So if the mu kappa independent spectrum is non-empty, then 2 to the less than mu equals mu. And there are some weak kind of large cardinals. So there's a weakly monocardinal somewhere between mu and lambda. It could be equal to mu, but if you start with some mu that you know is small, then it's going to be very large, much larger than mu. Okay, there's this weakly monocardinal lambda, and a lambda complete ideal I on kappa with p kappa mod I is forcing equivalent to adding theta many subsets of mu, where theta is the size of some maximal independent family. I should say also another consequence is that 2 to the mu is, let me just write that, also 2 to the mu, this is too thick. 2 to the mu is greater than or equal to lambda. So you get some GCH, and then you get a potentially very strong failure of GCH. And so the theorem we have that uses this approximation property is, not only is it unusual to have non-empty spectrum, but it's very fragile. So if mu is a regular cardinal and p is any non-trivial forcing that's either of size less than mu or satisfying the nu CC for some smaller cardinal nu, then p forces the mu kappa independent spectrum is empty for all kappa. I guess I should mention, maybe it's easy to see from the definitions that kappa must be at least mu for this independent spectrum to be non-empty in the first place. Okay, so there are 2 key cases that we prove separately. So we know from Kunin that if you were to have a non-empty spectrum, then you'd have these ideals lying around that are equivalent to Cohen forcing. And so if you have this ideal and the completeness of it is lambda, then there are 2 possibilities, each of which is consistent. You can have mu less than lambda or mu equals lambda. And we're going to rule each one out. So assuming you take a generic extension by p of this kind, and then you want to prove by contradiction that there's no such maximal independent family. The argument for mu equals lambda to rule that out is very similar to the argument for Hampkin's superdestructibility theorem, and it's written in our preprint. So I want to describe the other case, which is a bit different. So, okay, so we're in the other case. We can weaken the assumption. So P can have the strong mu CC. So it doesn't have to be smaller than kappa or smaller than mu, or having a even stronger chain condition. So yeah, and in the case mu equals lambda, you do need that. So here's the argument in outline. So suppose this failed, then by Kunin, you would have some ideal J on kappa, uniform ideal, where p kappa mod J is equivalent to add mu theta for some theta. Okay, and it has this ideal J. I don't know if it's normal or not, it doesn't matter, but it has some completeness lambda. And in V, let's pull it back to an ideal in V. So just I is the set of subsets of kappa that are forced to be in J. And I should have introduced, oh, I did introduce lambda here. Okay, so yeah, we can show that this pullback ideal has the same completeness and saturation properties as J is forced to have. So I bar denotes the ideal generated by I in VP. And since I is the set of things forced to be in, so more specifically, the things that are covered by members of I, that's all. And I bar, by similar argument, since P has a very nice chain condition, I bar will be lambda complete and mu plus saturated. And by the definition of I bar is contained in J. And there's a general argument dating back to the 70s by somebody, maybe Baumgartner, I forget, that so you have a saturated ideal I bar and you have some larger saturated ideal J. J is actually just a restriction of I bar to some positive set X. Okay, so we have a more concrete description of J in terms of a ground model thing. Now the key claim is that this P kappa mod I in V is mu distributive. So I'm not going to give the argument for this because it's just a little bit technical, but I'll just say that, well, we know since P kappa mod I bar restricted to X is just P kappa mod J in VP, that's co-enforcing, so that's mu closed, right? That's going to be mu distributive in VP, but how do you show it's actually this P kappa mod I is distributive in V? So to prove this, we use Fourman's duality theorem, which gives us a kind of, it gives an isomorphism of precipitous ideals, so you can kind of describe their structure, the structure of the generated, the algebra of the generated ideal. And so there's the duality because you have this very nice sort of switching the order of things equation. So P star, P kappa mod I bar is the two-step iteration is isomorphic to the two-step iteration forced with P kappa mod I and then forced with J of P, where J is the generic ultrapower embedding associated to this guy. I should say, in case you haven't seen this before, you can compute a lot of things by taking I to be the dual of an ultrafilter. So in that case, you can kind of ignore this part of the equation and then you can say, well, I can choose many P's. I mean, it has to satisfy some hypothesis like nice chain condition or existence of master conditions. Then you can describe what this guy looks like pretty concretely. Okay, so there's this equation. There's also some information. You have the possibility of taking two ultrapowers. You can, so if you take a generic for this two-step iteration, then you'll have the generic ultrapower of V by this, and then you'll have generic ultrapower of VP by this. And there's a relation between them. So actually, let's say, M0 is the ult of V by, so let's say this is G and H, and this is H prime and G prime. So you can, so let's say this, you have this, and M1 equals ult V H prime by G prime. So then actually M1 is just M0 adjoin H. So this is quite useful. Okay. All right, so these are the ingredients. Okay, I'm not actually giving you a proof, but these are good things to know about. So, okay, so the point is what we just, we use this stuff to somehow prove that this is distributive. So let's see the conclusion of the argument. So there are two cases to consider. The first one is kind of an easy case. So maybe P kappa mod I was actually a trivial forcing below some condition. That means that below there's some positive set such that I is a maximal ideal on that power set. So the dual is an ultrafilter on B there. Well, in that case, Fourman's duality theorem tells us that, as I mentioned, this sort of easy case where you can drop off a trivial forcing power set of this B mod, the generated ideal is just J of P mod G. Now P was non-trivial and mu CC, right? So because mu is actually less than the completeness, this equation, you have to translate between the ultra power and the generic extension, but you get it that I bar restricted to this B is forced to be mu saturated, but this is just false because PA, that's a kind of relic of an older version. So P kappa mod I bar is equivalent to, or at least, yeah, sorry, maybe it's important. The A is some restriction. So there is some A, there is an A, such that P kappa PA mod I bar is forcing equivalent to add mu theta because we had this hypothesized J, this ideal, and we found that J is actually a restriction of I bar. It's equivalent to adding mu coens, and this is mu closed, not mu CC, nowhere mu CC, so this case is ruled out. Okay. The other possibility is where we actually use the approximation property. Okay, so it's a non-trivial forcing. It's mu distributive. Let's take a generic for these two steps. So P kappa mod I star J of P. So again, so this is the one side of the Fourman duality equation. So since this is distributive, H, the generic H itself has the property that H intersect A, little a, is in V for all A in the power set of this forcing, the P mu of this forcing from V. Because this would be also a small set, a set of size less than mu, and the forcing doesn't add any of those. Okay, now this two-step extension can be written another way using the duality. So we have this way, and then we had the P star, the generated ideal, or which is the same as this J, this P kappa mod J in the extension. And that was P star mu coens. So this is a strong mu CC forcing star mu closed. So Usuba's theorem says that the two-step iteration has the mu approximation property. So this two-step iteration adds some generic thing H, which is approximated by P mu, the background forcing of V. So the property says that H is in V, but it's a generic for a non-trivial forcing, so that's impossible. Okay. Am I supposed to have just till the hour?
Oh, no. You can go 1.5 hours, as much time as you want.
Okay, I'll go ahead and finish the third part then. Sorry, was there another comment?
No, I
So,
was just gonna say whatever Gunther said, that you can have as long as you want.
Okay.
are you done with this part?
Yes.
Could I just ask a quick question?
Yeah.
It's just about the motivation of the concept of maximality that you use. So you're saying, such a family is maximal if when you add an extra set, you're not even independent anymore, right?
Yes.
And it seems like that's the strongest sense in which the strongest requirement you could make. You could also weaken it and say it's, say, lambda maximal if when you enlarge it, you're not lambda independent anymore for some lambda greater than 1 or something like that. Did anybody look at that, or is it like just looking at it for the first time, it seems like why do you choose this extremely strong sense of maximality?
Yeah. Yeah. I mean, the reason is kind of that we can prove things about it, but so Kunin has a slightly different approach to the definitions. He says, instead of introducing this kappa parameter, just call it, mu maximal independent family. So we don't know about the cardinality of the intersections or the Boolean combinations, but he shows that there is some restriction of this family that's uniform. So there's at least going to be some, not necessarily not a subfamily, but like there's some subset of the background set where you can intersect a subfamily of this original family with that. I mean, point wise, and then you'll get something that's maximal. That's mu kappa MIF, like according to this definition. So, right. Yeah, why not just say it's maximal with respect to its defining properties? I mean, it's worth thinking about. I think when I was writing the paper, at the beginning I thought about this a lot, and just sort of went for the most elegant definitions that sort of made the math work. And so it's not a really great answer.
Right.
But
no, but it's good. I mean, it sounds like there might be some variations that one could think about, like, vary the degree of maximality, but just, maybe being a little more liberal or something like that.
Yeah, there's certainly things to explore there.
All right, okay, thank you.
Welcome. Okay, the third topic, unless there are other questions about the second one. So the third topic is about a short paper of mine where it took me a while to come up with the argument, but then I want to give it completely right now. It should just take 15 minutes or so. So in the Handbook of Set Theory, in Matt Fourman's chapter, there's a section at the end that's more philosophical, where he talks about, the chapter is all about generic elementary embeddings. And for many years, he had thought about very strong kinds of these things and their many combinatorial consequences. And he discusses the idea that these could be axioms, of a similar worth as considering for axiomhood as traditional large cardinals. I mean, he doesn't and without trying to insult him at all, he doesn't like spend a lot of time like doing a philosophical analysis of that, but he makes a proposal. And it's interesting because it's like, here's some principles and they look very elegant to state and they have many consequences. So, I mean, the one main motivating example is, well, here's here's an instance of one that implies the CH and implies like it solves the Suslin problem, says there exists a Suslin tree, for example, and some other things about infinitary graph theory that were asked by Erdős and some co-authors. So, okay, so it's an interesting idea. So anyway, he defined some specific versions of these things, and he called them minimally generically huge cardinals. So there are properties of successor cardinals, and so if you have successor of a regular cardinal mu, we say kappa is minimally generically huge if the simplest collapsing forcing that you can think of, col mu kappa, forces a generic embedding with critical point kappa, I should say. I should have said into a transitive class contained in the forcing extension that's closed under J of kappa sequences from the forcing extension. So this is strongly analogous to huge cardinals in the definition. And the minimality is just that this is forcing, like consider the case kappa equals omega 1, then this is like the smallest forcing that could be used for generic Hugeness of omega 1. In the more general case, it's the forcing of smallest size, but it's also maybe the simplest one. But I'm going to exploit the fact that when you consider mu greater than omega, you're also introducing a closure assumption on the forcing. So then we get into some problems. So if you want to drop that, I mean, there's still maybe an option for exploring minimal generic Hugeness in the sense of just smallest density of a forcing. If you're still interested in this kind of philosophical or foundational project, that I can't at present rule out anything there. So what is actually the result? Okay, still I need some definitions because there's a more general result. So I think these are natural definitions for stating what we can prove more generally. So we'll say a cardinal kappa is for a poset P and a cardinal kappa, kappa is P generically huge to lambda. If P forces there is an elementary embedding that's into a transitive subclass of the forcing extension, this sends kappa to lambda, and M is a transitive class closed under lambda sequences from VG. Notice I didn't actually say in this definition that kappa is the critical point, and the arguments won't need that. So I think this is a reasonable enough use of the terminology huge to lambda. Okay, and then a more prevalent situation is, we'll say kappa is P generically measurable if P just forces that there is some elementary embedding after forcing with P with domain V, and the critical point is kappa. Okay, so the theorem is that these generic large cardinal properties contradict each other in specific instances, and in particular, a cardinal and a successor both being minimally generically huge. And there was some precursor of this using the notion of generic N Hugeness, which is defined the way you think it is supposed to be. And Wooden showed that in an unpublished note that enough N Hugeness, like of nearby cardinals, will reach a contradiction. So this is getting down to just one Hugeness. Okay, so the theorem is, suppose kappa is a regular cardinal that's P generically huge to lambda, and P is non-trivial and strongly lambda CC. Then kappa plus is not Q generically measurable for a kappa closed Q. So again, the closure would come from that, like setting the collapse being col kappa plus, next step above. Okay, so let's
Sorry,
see the
Monroe.
yes.
You always mean that kappa is the critical point of these embeddings, right? Or
That's the intention, but
okay,
the argument actually won't need that kappa
see.
is the critical point. Yeah,
I see. Okay.
we just need to know where it goes and the chain condition. Okay, so this is not just an outline, but more or less complete argument, and so let's try to just get through it. So, okay, so we have these two notions that are not necessarily written in a first order way or just in the language of sets. But let's just substitute the second one, the generic measurability, with something that's definitely first order, because we're going to apply elementarity to it, to that thing itself. So a weaker version is just restricted to some set embedding, set sized embedding. So let's say Q is a kappa closed poset, and for some large lambda theta, much larger than lambda, Q forces an elementary embedding with domain h theta v into some transitive set with critical point kappa plus. There's no need for a 1. Okay, so first, this is a relatively simple argument, actually. The assumption of the closure of Q gets you some GCH at or near kappa. So we have kappa to the less than kappa equals kappa. So the reason is just that it's a kappa closed forcing. The critical point is kappa plus. So if you look at p kappa of v, you're not adding anything to that, but the embedding, if this thing had cardinality, at least the critical point, it would stretch an enumeration into something longer. So you would add sets. So since it's a kappa closed, we don't do that. That means the cardinality of this must be below the critical point, which is the only possibility is that it equals kappa, of course, for another reason as well. So, okay, now the next claim is that now using the Hugeness embedding. So this part uses, of course, just the generic measurability embedding for kappa plus. Now we apply elementarity with the Hugeness embedding to move GCH up to lambda. So the argument is just this. So if you take a generic for P and take a generic an embedding as in the hypothesis, then we know that so M is closed under lambda sequences from the extension. So in particular, less than lambda sequences. So it has the same P lambda lambda as VG. Okay, so by elementarity, so kappa goes to lambda. So M satisfies that, so you have kappa equals lambda. So M satisfies that lambda to the less than lambda equals lambda. If it weren't true in V that that lambda to the lambda equals lambda, then we'd have some, then we would collapse lambda plus. So the argument is, so M has some surjection onto P lambda lambda of the full extension, which contains P lambda lambda of the ground model. And if this has size at least lambda plus, then it would collapse lambda plus. But we're assuming that the lambda CC holds. So, okay, so we have these two instances of GCH. Okay, I'm going to use that just to show that the closure of M implies that we can define this local approximation. So the property of being approximated, not the approximation property. So let F be this, the P lambda lambda of V. We have an elementary embedding as hypothesized, J from B to M. This is the generic Hugeness one. So because lambda to the less than lambda has size lambda, F is coded by a single subset of lambda from V, and that's a member of M. So this collection script F is in M. Okay, now in M, let's define what it means to be approximated by that collection. So let's take script A to be the collection of all subsets of lambda that are approximated by F. Okay, so I guess the significance for like this technique in the argument is we're able to talk about stuff, a lot of stuff that's going on below lambda plus, kind of using only things of size lambda. It's like M doesn't really know what, I mean, there might be many subsets of lambda plus that M doesn't have, but we can kind of get at it with this approximation property, enough of it. So this is what allowed the argument to be the degree of Hugeness to be lowered. So, okay, now M has every subset of lambda as a member that's from V or VG, right? Not this set as a whole as a member, but it's at least a subset, not necessarily, right? So because it has every one of them, each ordinal less than lambda plus is, so M and V and VG all have the same lambda plus. And in V, there's some surjection from lambda to a particular ordinal alpha less than lambda plus. So M sees the shadow of this in the sense it says, I see that there exists an X alpha that is approximated by F, so it's in my collection script A, and it's coding a surjection from lambda onto alpha via the Gödel pairing or whatever coding scheme you need that's absolute enough. So M, right, it doesn't really know like what, it doesn't have that object, whatever, but it says I see this property. So working in M, I choose a surjection that's approximated. For each alpha, I choose a surjection from lambda to alpha. Okay, so now by elementarity, right, remember that V says kappa plus is Q generically measurable. Kappa goes to lambda. By the closure, kappa plus goes to lambda plus. And M says that lambda plus is J of Q generically measurable. And in this setwise sense. So domains with embeddings, embeddings with domain, the H J theta of M. By the closure of M, J of Q is a lambda closed forcing. So again, we only really need a less than lambda closure. The full closure is not really needed. I'll just remark that at the end, but we sort of called upon it to just say this part, right? It has every subset of lambda from V. Okay, now, so you have something that M thinks is lambda closed. It really is lambda closed in the extension because of the closure of M. So let's take a generic H for it. And that comes along with a generic embedding. So, you take this H, adjoin it to M. M says, in my generic extension, there's this thing. And the critical point is lambda plus, which I just called delta. Okay, now, here's the thing. So the critical point is lambda plus. You have this sequence of X alphas that are coding surjections from lambda to the alphas below lambda plus. It gets stretched out, right? So point-wise, each of these is unaffected, but it gets longer as a sequence. So there's one at the place lambda plus of V, which is this delta. So there's an X prime sub delta. And by elementarity, it's also approximated by F, which is I of F, because again, F itself has size less than the critical point. Size of F is, sorry. I like to do my script Fs that way. Size of F is lambda, which is of course less than this delta crit J, crit I. Okay, so what is it then? We have a two-step iteration that's strongly lambda CC and then lambda closed. And by Usuba's theorem, this forcing extension has a lambda approximation property. So here's a set that's approximated. It must be in the ground model, right? But this is a contradiction because this set codes in some absolute way surjection from lambda to its index, which is the lambda plus of V. So this is the end of the argument. And I'll note that we only used that the ground model power set of lambda is a subset of M. So we don't even need that the P lambda VG is a subset of M. But we just need that and that M is lambda closed in the argument at least. I mean, I can also say something about the optimality of the argument is that like if you drop down to a notion of generic almost hugeness, then you can, well, it will have this amount of closure, and it typically will not have this property. And the situation is, it's consistent relative to at least a huge cardinal that omega 1 and omega 2 are minimally generically almost huge, if you can see what the definition is supposed to be for that from con ZFC plus exists huge. Okay, so that kind of shows a boundary to the argument in some sense. Okay, so this is all I wanted to talk about. So as I said, this is from 3 works of mine, 2 of them joint, and they're all on the archive. And I thank you very much for your attention.
Thank you very much for the talk.
Thanks
That
very
was
much,
great.
Monroe.
There were a lot of questions already during the talk. Are there more? Does anybody have more questions? Now would be the time.
Now, I have a general question.
Mm-hmm.
Early in the talk, you mentioned Suslin trees, Kappa plus Suslin trees. Now, when you go back to the original Suslin trees, of course, they're connected up with characterizations of the continuum. And so they emerge somewhat naturally. But what is it about Suslin trees that makes them relevant when you're talking about large cardinals and these issues you're addressing? What is it magical about Suslin trees? How do they come into it?
I mean, they come into to Usuba's proof via, he says, if you so you can think of it as a proof by contradiction. So it's like, suppose you have after you force with P star Q, you have a set that is kappa approximated, but it's not in the ground model. So using the combinatorics of the forcing P star Q, I mean, he shows that you build a Suslin tree. So the kappa CC of P is used to kind of make sure the levels of the tree don't grow, and then the fact that Q is kappa closed kind of allows you with some term space argument to kind of choose elements of Q dot to like continue along, keep building in the tree. So you kind of have many choices for the initial segments of this set, but not too many, because you have a tree of choices that ends up being a Suslin tree. And so that's the significance. And then he says in the end, well, if you do the forcing, so here's a Suslin tree. I mean, he defines it in the ground model using the properties of the forcing. Okay. Mm-hmm. And then he says, if you look at the decisions that the generics make for this set you added, like just the partial decisions before you force with Q, well, then you must be adding a branch through that tree after forcing with P. Okay. So mm-hmm. But this assumption is that P doesn't add branches to kappa Suslin trees. Yeah, so I mean, this is how the argument works. Mm-hmm. I mean, I don't know if kappa Suslin trees in general have a kind of connection to a generalized continuum. Maybe someone can say something about that. But they are kind of like combinatorially remarkable objects, I guess. So, right, I mean, yeah. That's all I can say.
Thank you. No, I mean, that's well put. They're combinatorially valuable.
Yeah.
Okay, any further questions? Anybody? Okay, seems like everybody is satisfied. Well, thanks again for the very interesting talk. It was really cool, this potpourri of applications of this technique. So thank you very much.
Thanks very much. It was a pleasure.
Thanks, Monroe. Thank you.